So in the last lecture, we did see that when we put beta is equal to 0 in this final expression, we actually get a relation which will be simple harmonic in nature. We are going to get a cos function or a sine function. Today we are going to analyze the second case where we are saying that beta square is less than omega naught square. And here we are going to see that it will be oscillating in nature. So we'll be having the sine and the cos function. But along with that, there will be damping. That means the amplitude is going to die off eventually. So let's see how we are going to derive this particular case. So this was what we did in our last class, and we did see that we are actually having a cos function with an amplitude e, which is constant. In today's class, what we are going to do is we're going to take up the next case. So let's discuss case 2 for today. So let's take case 2. So the case 2 is, as we have already seen, it's beta square is less than omega naught square. Or more specifically, what we can write is b square is less than 4 km. You can refer to the last 2 or 3 lectures in order to come to this conclusion. And here, what we are going to do is we are going to do an assumption, and the assumption is let omega 1 square be the difference between these two terms. So here we basically have omega naught square is the larger term, beta square is the lower term. So maybe I can do it like this: omega naught square minus beta square. So we're replacing this nth term with this, and then expression 2 will take up this form. So you can refer to the expression 2 which we have been using, and this will become something like this: xt is equal to e to the power minus beta t. In the first case, we put beta is equal to 0. This time beta does have a value, so we're not going to put it as 0. This was c1 e to the power. Let's just check expression 2 here. So we can say beta square minus omega naught square. Now omega naught square is greater than beta square, or beta square is less than omega naught square. So you take a root of that. That means you're going to get a negative value. That means you can have an imaginary function here. So that I would be there included, right? So if we simplify this further, that minus term under the root will be represented by I, and beta square minus omega naught square is equal to omega 1 square, and there is a root. So you can simplify it, you'll just get omega 1 into t. So we're replacing it in expression 2, then we can take a plus, then we have got c2 e to the power, there was a minus there, minus I omega 1 into t. So please refer to expression 2. You can practice it and you will see that you're getting this answer, right? Now we are going to do certain assumptions to keep things simple and simplify it easily. So we are going to assume that this term c1, of course, it's a constant, so I can take it in any form that I like. Okay, I can write it as half c e to the power I theta. Theta, let's say it's a constant angle, and I can write it down as half c e to the power I theta. In a similar way, I can also assume c2, and I can write it to be half e, or I can write it down in terms of c, and the second term c2 would be half c e to the power minus I theta. Now, as you can guess, we are going to replace this c1 and c2 here, and let's see what is the form that we are getting. So therefore, we can say xt is equal to e to the power minus beta t remains the same. We have c1, c2. The common term is half c in both the cases. So let me just take out half c out of the bracket. And now I can put everything inside the bracket. We have the term e to the power I omega 1 into t, and in place of c1 we can write it down as e to the power I theta plus, again I have the term e to the power minus I omega 1 into t into, in place of c2, and write it down as e to the power minus I theta. So certain arrangements we have done here, and we can see, we can simplify this. Let me write it down as c e to the power minus beta t into half. Put the bracket. We have got the bases are same, powers can be added. So I can write it down as e to the power I. Let's take it common. This would be omega 1 t plus theta. Simple maths here. And then we can write it down as e to the power minus I, and then again omega 1 t plus theta. Now we do know a result, and let's use that result. Okay. The result is of course something you might have come across before. I will take it as e to the power ix plus e to the power minus ix divided by 2, and that is nothing but equal to cos of x. So that means this term can be written in terms of cos. You see, I is there, minus I is there. In place of x, we have got omega 1 t plus theta, and there is a divided by 2 there. So can we write it down? Yes, we can, right? It's simple. So we can write it down as c e to the power minus beta t into cos. This entire term can be written in terms of cos x. So x is, in this case, is omega 1 t plus theta. So you see here, we basically do have an oscillating term which is going to give you that motion. So this first, the second term, cos of omega 1 t, is the oscillating term. And this term, you basically see is a constant, right? And you know, there is an exponential term, which is the coefficient of the cos term. And we have seen whatever is the coefficient of the cos term is basically the amplitude term. And this is more or less exponential in nature. So this is exponential, but there is a minus sign in front of this. So this is basically a decay. That means, I hope you get this. Let's say beta is constant. If t increases with time, this entire value will decrease because there is a minus sign, right? So if you write it down something like e to the power minus x, you can write it down as 1 divided by e to the power x. That means if x increases, that means e to the power minus x will decrease. There will be an exponential decay. So this is the term that we are basically getting, or the displacement that we are getting for the second case. Please remember, this is very important because eventually we are going to use this more and more to understand things better. We can in fact, also draw a picture here. We can, let me just take up the axis. And now you have a wave. That means you can plot the cos term, right? But then it decays exponentially. So, be it along the x-axis, sorry, the y-axis positive or the y-axis negative, this is going to decay. So if you want to really plot the graph for this, even if you check it experimentally, you're going to get, it's a cos term, so it will start from the maximum point, 1, and then it's going to, slowly reduce in amplitude. So this decay is the exponential decay that we have. So, this term which we have, or this image that we have, that is representing the cos term. So maybe I can write it down as cos term, okay? Or we can say the oscillating term. and it's reducing in amplitude. So obviously there is a decay in this. So this decay is actually representing the amplitude term, right? So we can write it down as c e to the power minus beta t. And since this is controlling its amplitude, it is also known as the modulating term. This is the modulating term. Okay, so that's important. So we do have two terms here. One is the constant, which is actually giving you this waveform, oscillating term, and this exponential term is the reason because of which the amplitude is dropping, and we have got the modulation here, right? And what we call this is, as I've already mentioned, this is nothing but under damping. So if you're asked a question based on under damping, you're supposed to, they have this particular relations. Okay, what happens in under damping? I think it's quite obvious now. Oscillations are there, of course, there are oscillations. Oscillations are there, but it reduces with time. So that's it for today's class. In the next class, what we're going to do is we're going to check for the next condition, that is beta square is equal to omega naught square.